right. As far as pacing goes, we want to try to get these done, say 10 minutes would be a good target time for something like this. Although this is a little longer problem, so maybe 15 minutes or so. But the first thing you should realize is if you're given the quantities of two reactants, it's automatically what type of problem. If you're given, let's say, methane and the amount of oxygen, both of those amounts, then it's automatically a limiting reactant problem. And so the first thing to do is we have to figure out which one is the limiting reagent. Is it the methane or is it the air? Which one is the limiting reagent? It turns out in this particular problem, I wrote the methane first because a lot of people automatically go to the methane first and then calculate it based on the methane, but it turned out it wasn't the first one that was the limiting reagent. The methane was the excess reagent. The limiting reagent is the air. There wasn't enough air to burn all the methane. And so you would have had to do a calculation to show that. But you should recognize whenever you're given quantities, if we were only given the methane, then that's fine. You could assume there's plenty of air. But since we're given both, the other thing is water a gas or is water a liquid under these conditions? Water is a liquid under these conditions. And so we can't use the simple thing that we did yesterday where we just take the volume ratios. What we have to do is we have to figure out how many moles of water forms and then convert that from moles of water to grams of water and then go grams of water to milliliters of water. And so based on air being the limiting reactant and that we're forming liquid water, the amount of liquid water we should form is about 178 milliliters of liquid water. In that case. And so that was the answer to that problem. I'm going to give this one back. We'll look at it after I give it back. So this was a tough problem. It wasn't so easy. All right, we're going to talk about the chapter 17 next, which deals with acids and bases. This chapter is focused on Bronsted acid-base reaction. Bronsted acid-base reactions, the acid is a proton donor, the base is the proton acceptor, so we call it proton transfer. Proton's just an H plus ion. So that's what I said. What were the three definitions of acids and bases? Well, the first one we covered was the Arrhenius. Arrhenius is not that useful, it's just H plus. Arrhenius acid is anything that gives H plus in solution. Or contains H plus. Base is OH minus. Arrhenius acids H plus, Arrhenius base is OH minus. That's basically it. It's not the most useful definition of an acid and base. Much more useful acid and base definition, the Bronsted and the Lewis. Which one is more comprehensive, Bronsted or Lewis? Lewis. Lewis is more comprehensive, but it's a bit more tricky. Yeah. So we're gonna, if we can classify it as Bronsted, it makes life easier. Those are like the chemical definitions, but there have been other definitions of acids and bases. Acids tend to dissolve carbonate, like coral here. Piece of coral, dead coral, hopefully. It's mostly calcium carbonate dissolves in acid, bubble off CO2 gas. So acids react with carbonates to generate carbonic acid, which decomposes into CO2 gas. Acids react with certain metals, like zinc, aluminum. Acids react with what we call active metals. That generates hydrogen gas over here. Acids change the pH of water. The pH of water becomes more acidic. We can tell based on like the dyes and what we call indicators. And so red cabbage juice can change color depending on the pH here. So at more acidic conditions, it's this color. At more basic conditions, it's this color. So the cabbage must be pretty what? Look at the color of the cabbage. It must be, the cabbage itself must be acidic or basic? Acidic. Well, Bronsted-Lowry is going to be very useful for us. And so a Bronsted base does not have to contain hydroxide. So for example, ammonia, there's no hydroxide there, ammonia, but this is a base. So this wouldn't fit the Arrhenius definition. Arrhenius would need hydroxide. And this would be our Bronsted acid, water. And so all we do is the base accepts a hydrogen, the water loses it. So if the base accepts it, then we're going to get 4 hydrogens on here. The 4th hydrogen is an H+. So we're going to form NH4 plus ammonium. And this water is going to lose the H+, leaving behind the lone pair, so we'll form hydroxide, ammonium hydroxide. So this is a Bronsted acid-base reaction. Ammonia plus water gives ammonium and hydroxide. However, this reaction is not so favorable. It's not so favorable because we're going from a weaker acid to a stronger acid. Ammonium ion is a stronger acid than water. And we're going from a weaker base, ammonia, to a stronger base, hydroxide. And so this reaction is not favorable. However, it's an uphill reaction. However, there are a small population of ammonia and waters that can actually react and make it up here, the product. And that very small population is what results in metathesis reactions being used in, ammonia being used in metathesis reactions. And when we do ammonia in metathesis reactions, we take ammonium plus water to give us ammonium hydroxide. So this is ammonium hydroxide we use to figure out the products of metathesis reaction. And so even though this reaction is not very favorable, a little bit does form enough to have a little reaction occur there. It's acid-base reaction. When we look at these species, some of these can go either way. For example, ammonia can act either as an acid or base. Water can act either as an acid or base. We have lots of amphoteric species. Amphoteric species can go either way. And so what it depends on is who's the strongest. Whoever the strongest acid present is, that's going to be the acid. And who's the strongest base, that's going to be the base. And so some species are amphoteric. They're both acid and base, but their role is dictated by the other species in the solution. We have forward reaction, reverse reaction. So we look at these as competitions between forward reaction and reverse. Which side's stronger, which side's weaker. In other words, like a seesaw relationship. And so water can either act as an acid or a base. In this case, it's acting as an acid. Why? Because we have ammonia, which is a stronger base. So the strongest base present is ammonia, and the strongest acid present is water. So that's the roles they take. Sometimes ammonia doesn't even act as a base. Sometimes it can act as an acid. Well, this reaction is reversible. For sure, this reaction is reversible because very little forward reaction occurs. This reaction is tilted like this. So you have a small population of highly energetic species that can react and go up here, but the amount that we form is very small because most of the populations here, the reactants are more stable than the product. It doesn't mean that no product forms. A little bit of product can form. It depends on how steep this is. If this is like this, then pretty much no reaction occurs. It's just too steep, but the less of a difference, the more product that can form. And then if the products are favorable, then it tilts the balance towards the product.
So whichever acid or base is strongest is the one that's going to get the hydrogen?
Yep. Yeah. it's the ones that are going to react. Well, we're going to see this here. All right, Lewis acid base. You know, when we look at this BF3, they're missing the lone pairs here, by the way. BF3 doesn't have an octet around boron, and so BF3 turns out to be good Lewis acid. Lewis acid because it wants the octet. One way to get the octet is reacting with Lewis base. Lewis base is an electron pair donor. And so if this electron pair is donated to this boron, then we form boron, nitrogen, single bond here. Now boron has an octet. Nitrogen has an octet. The only thing that's screwed up are the formal charges. The formal charge on boron goes to -1, and the formal charge on nitrogen goes to +1. So the formal charges get screwed up, but we get the octet. This would be an example of a Lewis acid base reaction here. It's not as easy to visualize as Bronsted. But for sure, the Lewis is the most comprehensive. We only need one definition to Lewis, but Lewis is a bit more conceptually difficult. And so we like to think in terms of Bronsted when possible, then switch to Lewis when that's not possible. Arrhenius, we don't even bother. So when we do this, we're looking at proton transfer. So let's look at the mechanics of the proton transfer reaction. The acid's going to lose it. The base is going to accept it. And the acid loses an H+, the base accepts it, so we're going to form HB with a positive charge. In other words, this charge is going to go up 1. The base might be negative, like hydroxide or something like that, and then it goes neutral. So this just means the charge goes +1. And then, of course, the acid's going to lose an H+, so we're left with this, A-. Now, in the forward reaction, what's the acid? HA is the acid. What's the base? B is the base. Then we step over on this side and say, okay, we're going to reverse this reaction. What's the acid? Well, HB+ is the acid, A- is the base here. And what we're looking at is we're looking at the competition between the forward and the reverse. The way we look at the competition between the forward and the reverse, which direction's favored? Well, the downhill direction's favored. And we got to figure out which way is downhill. And then we get to figure out if it's downhill this way, then the forward reaction is favored. If it's downhill this way, the reverse reaction is favored. If the reverse reaction is favored, then if you mix the reactants, then nothing should happen. Or very little should happen because the reactants are more stable. All right, the different ways we could do this, but one of the things we look at are what we call conjugate pairs. So for example, if we have an acid on one side, it forms a conjugate base on the other side. And so HA and A- are called a conjugate pair. A conjugate pair is like this. When we have a conjugate pair, if the acid's strong, then the base has got to be weak. Or if the base is strong, then the acid's got to be weak. That's it. The conjugate pairs, it's easier to see in a relationship like this. Let me show you. Piazza, I have an acid strength chart. So if you go to Piazza, and then take a look at the handouts. One of the handouts is this chart here. Okay, these are conjugate pairs here. And this is why we only need one chart. We have a chart here. Okay, the strongest acid on the chart is HClO4 minus, HClO4, sorry, no minus. HCl4 is called what? Well, you usually get rid of the hyper and just call it perchloric acid. If perchloric acid loses an H+, it forms this, what's the ion called? Perchlorate. So it turns out the strongest acid is associated with the weakest base. This is the weakest base on the chart. And this is what we call a conjugate pair. If the acid's strong, it means it can lose the H+ easily. Well, what do bases want to do? Bases want to gain an H+. So if the base is weak, then that means the acid's going to be strong because perchlorate doesn't really hold on to the H+. It can lose it easily. HI, strong acid, iodide, weak base. As the acid gets weaker and weaker, what tends to happen is, the anion holds on to the H+. So let's go to some of the weaker acids down here. When we look at the weaker acids, like bicarbonate, let's say, it's because carbonate wants that H+, and so the weaker the acid becomes, the stronger the base becomes. So this is a conjugate relationship. So if hydroxide is a powerful base, but it's amphoteric. Amphoteric means it can go either way. So hydroxide is an extremely weak acid. Therefore, its conjugate is going to be an extremely powerful. And so if this is extremely weak, this is extremely powerful. Extremely weak acid, extremely powerful base. Well, hydroxide occurs on both sides of the chart. All amphoteric species will occur on both sides of the chart. So hydroxide is amphoteric, bicarbonate is amphoteric. Bicarbonate can act as an acid, as it does here, to lose a proton to form carbonate. But bicarbonate also acts as a base to accept a proton, as shown here. If bicarbonate accepts the proton, it forms carbonic acid, which decomposes into CO2 and H2O. Carbonic acid in quotation marks here. And so we have the conjugate relationship here, and that conjugate relationship means we only need one chart for both the acids. The strongest acids are up here on the left. The strongest bases are down here on the right. So we don't need the conjugate relationship really for this. Is there a driving force for this reaction? So this is CH3COOH. Do you know what that's called? CH3COOH. COOH. It's is it a alcohol? An alcohol? Turns out it's a acid. Yeah, it's an acid. This is an acid. This is called acetic acid. This is a different way of writing the formula for acetic acid. So we take acetic acid and water. In this case, what's the strongest acid present? Acetic acid or water? Acetic acid. Now that leaves base. What's the strongest base present? Well, the strongest base present is going to be water. Water can go either way. You can either accept a proton to form hydronium or lose a proton to form hydroxide. So water goes either way. In this case, the strongest base is going to be water. And so what that means is that water is going to accept the proton to form hydronium, and acetic acid is going to lose the proton to form acetate. And so what we do is we do this. We look at this. Is there a driving force? So going forward, what's the acid? The acetic acid. If we go backwards, what's the acid? Who loses the hydrogen going backwards? Hydronium. And so what's a better acid? Acetic acid or hydronium? So we need to consult the chart here. Okay, where is hydronium? Hydronium's here. Where's acetic acid? this is not, it looks like acetic acid, but it's not. You know why? Acetic acid is CH3. This is CCl3. There are 3 chlorines. That's trichloroacetic acid. Trichloroacetic acid is fairly strong. There's acetic acid. Acetic acid is way down here. And so which one's a stronger acid? Hydronium or acetic acid? Hydronium is a stronger acid. So when we go back to this reaction, is this reaction favorable? Does this reaction have a driving force? No, because hydronium is a stronger acid, acetic acid is a weaker acid, so this is uphill. This being uphill, well, how steep is it? How steep of an uphill battle is it? Well, it turns out it's not so steep that a little bit can react. So if I have, let's say, 100, maybe let's go 10,000. If I have 10,000 acetic acids, maybe 1 out of the 10,000 can make it up the hill. Does that make sense? Because it has enough energy. And so what we say is this. Weak acids are weak electrolytes. Weak electrolytes partially ionize or partially hydrolyze in water. And therefore, weak acids can form small concentrations of dissociated. You guys remember that from the electrolytes? And so if I put a light bulb in there, it would light up just very dimly, because we get a small concentration of these formed. It's not terribly steep or nothing formed, but a little bit formed. What is a conjugate acid of ammonia? Well, if they want the conjugate, they just want, what is it paired with? So ammonia, if it's a base, then bases do what? They accept H+. So if ammonia is base, then it's going to accept that H+ to form, well, NH3 plus H+ gives us NH4+. And so the conjugate acid of ammonia would be ammonium. The conjugate acid of ammonia would be ammonium. We can see that in the chart here. If we look for ammonia, there's ammonia. So they want the conjugate acid, so ammonia must be the base. This is a pair. One of the conjugates is the acid, the other of the conjugates is the base. So ammonia is the base, its conjugate acid would be ammonium. Ammonia is a weak base, but it's decent, and therefore ammonium is going to be kind of a poor acid. What is the conjugate acid and conjugate base of bicarbonate? Now, bicarbonate can go either way. And so we think this. If bicarbonate's the base, then it's paired with an acid. If bicarbonate's the acid, then it's paired with a base. And so what we need to do is we need to make bicarbonate the base so we can pair it with the conjugate acid. We've got to figure out what the acid of the pair is. So there are 2 ways you could do that. One way is, what do bases do? Bases accept an H+. And so bicarbonate plus H+ yields H2CO3, which is carbonic acid. Okay, if we pair bicarbonate with a base, then bicarbonate must be the acid. What do acids do? They lose an H+. So if bicarbonate loses an H+, we form carbonate. And so we could use a chart to see this. Here. The right side is the base side, the left side's the acid. So if this is the base, then its conjugate acid will be carbonic acid, which is unstable from CO2 and water. Okay, the other pairs here, this is the bicarbonate, and it's going to be paired with a base. So bicarbonate must be acting as the acid. Amphoteric species are going to occur on both sides because they can go either way. If bicarbonate acts as the acid, it loses an H plus to form carbonate. All right, we look at the reaction with water. Strong acids have a favorable reaction in water. You know, like HCl and water completely dissociate. We could look at that as being an acid-base, Bronsted acid-base reaction by doing this. And so strong acids completely react with water. So HCl plus H2O. So this must be our acid, and water must be acting as the base. And so what forms this acid-base reaction? Hydronium and chloride. Now what we do is we look and pretend that this reaction goes backwards. If this reaction goes backwards, which one's the acid, which one's the base going in reverse here? Acid's hydronium. And chloride's the base. And then the next step is we got to figure out which way is downhill. Is the forward direction downhill, or is the reverse direction downhill? We need to figure out which way is downhill. And so what we'll do is we'll use a chart to do that. The stronger the acid, you know, the less stable it is. And so which acid's stronger, HCl or hydronium? HCl. And so this is downhill. HCl's stronger, hydronium's weaker. We're going from stronger acid to weaker acid, therefore we have driving force. And so what we say is that strong acids hydrolyze water completely, or strong acids ionize completely water. Let's compare that to a weak acid. Like acetic acid. This is another way of writing acetic acid here, the more common way in Chem 4. When we look at acetic acid, we have HC2H3O2 plus, okay, we're going to do this as a Bronsted acid-base reaction plus water. This is going to produce what? Hydronium and acetate. All right, going in the forward direction, which one's the acid, which one's the base? And water must be the base. Okay, going in the reverse direction, which one would be the acid, which one would be the base? Acid and base. And so in this case, when we look at it and compare, since I just did this, but I'll do it again. Which way is downhill, the forward direction or the reverse direction?
Forward.
Okay, so
No, sorry. The reverse.
yeah, if we look, this is a different way of writing acetic acid. same thing, C2H3O2, HC2H3O2. Well, anyway, hydronium's way up here, acetic acid's way down there. And so this is an uphill. Hydronium's way up there, acetic acid's way down here. Do you see that? However, it's not too steep of an uphill climb. It's not too steep. And therefore, we say that weak acids slightly ionized. Weak acids slightly ionized because even though it's uphill, some of them can climb up that hill. Some of the more energetic species. But the bulk of them are going to stay downhill.
How do you know the angle? Like,
How we know the angle depends on the difference here. In Chem 1B, we have a quantitative measure of the angle. Let me show you something here. We know the angle based on the difference, you know. Let's say one is way up here, the other's way down here. Yeah. But if the closer they are together, for example, HSO4 versus H3PO4, that's almost horizontal. There's very little difference. In Chem 1B, there's numbers associated with these. And based on the numbers, we can figure out how steep the angle is. And it's also not really visualized in that way, you know, this way. It's visualized a little differently in Chem 1B. All right, let's take a break here and we'll start.